Hello, and welcome to our lecture on Lagrange multipliers and constrained optimization. We saw previously a problem of trying to maximize the volume of a box. The details went like this. The material for constructing the base of the box cost $3 per square foot, and the material for the four sides cost $2 per square foot, and there was no top. It was an open box. And we had a constraint. We only had a certain amount of money. In fact, I made the constraint that we had $1,296 to construct this box. And we were looking for the dimensions of the box of largest volume given this constraint. Well, we'll solve this problem again using a technique developed in this lecture called Lagrange multipliers. This is a very powerful technique for problems that have a maximization or minimization theme, but yet have these side constraints. And we could have one constraint or even more. And one of the big keys to this technique is the use of the gradient of a vector that we developed in a previous lecture. The example of constrained optimization, I want to make sure we understand it. There's a function to maximize or to minimize, but there's a side condition, the constraint. And we have to take that into account when we try to maximize or minimize. But before we turn to the box, let me look at a simple example in the plane, an area problem. Suppose you want to find the rectangle of maximum area that can be inscribed inside an ellipse. And the ellipse will be x squared over 9 plus y squared over 16 equals 1. So here's a picture of that ellipse. It's a simple curve in the plane. And if we pick a point xy in the first quadrant, then the area of the rectangle formed by that xy and those four vertices would be 4xy. The area of the little rectangle in the first quadrant is xy, and then we have four of those rectangles, so it's 4xy. Now think about it for a moment. If x is near the x-axis and y is near 0, we would get a very skinny and not a very high rectangle. Or if x were near the y-axis, then we would get a tall rectangle. But the bottom line is, depending on where you place x and y, you get different rectangles and hence different areas. We want to find where to place x, y such that the area is as large as possible. So we're trying to maximize the area of that rectangle, and that's a function of two variables. F of xy equals, the base is 2x, the height is 2y, so we're trying to maximize the function 4xy. We want to maximize that. But there's a constraint. The point xy has to be on the ellipse. So that's the side condition that Lagrange multipliers takes into account. So I'm going to look at that constraint in the following way. Let g of xy be x squared over 3 squared plus y squared over 4 squared. Now, the constraint is that xy lies on a level curve of that function g. In other words, a level curve means set g equal to a constant. So if you set g equal to 1, we've got our ellipse, don't we? And the constraint is that the answer, xy, has to lie on that level curve of g. In fact, all the level curves of g are ellipses, aren't they? Okay, what about the level curves of the function f, which was equal to 4xy? Well, I claim those are hyperbolas. Here's the computation. 4xy equals a constant is a typical level curve of f. Remember how level curves work. You take your function, set it equal to a constant. So 4xy equals k implies that y equals k over 4x, or 1/4 of k over 4x. Okay, those are hyperbolas. Those are hyperbolas. For different values of k, those hyperbolas go up and down there in the first quadrant, as I've indicated in the figure. And you can imagine a hyperbola actually touching that ellipse, and that will be the optimal value. In other words, we want the level curve of f to be tangent to the level curve of the constraint g. Well, here's the key. If these two level curves are tangent to each other, then their gradients will be parallel. Remember, gradients are orthogonal to level curves. So if the level curves are tangent, the gradients will be parallel. They'll be multiples of each other. And that's the secret of Lagrange multipliers. The gradient of f will be a multiple of the gradient of g. So we write it as gradient f of xy is a multiple, and the symbol they use is the Greek letter lambda. Lambda times the gradient of g. Lambda is called the Lagrange multiplier. So here's Lagrange's theorem. I think we've got it all sort of set up now. Suppose f and g are nice functions, continuous first partial derivatives, and that f has a maximum or a minimum at a point x0, y0 on the smooth constraint curve g of xy equals c. Now, as long as that gradient of g is non-zero, there exists a real number lambda, the Lagrange multiplier, such that the gradient of f is lambda times the gradient of g. That's a great theorem and a very powerful technique. It's named after the French mathematician Joseph Louis Lagrange, who lived from 1736 to 1813. He introduced the method in a paper on mechanics when he was the ripe old age of 19 years old. Pretty amazing. Lagrange was also the mathematician who was the first one to prove the famous mean value theorem of elementary calculus. He was born in Italy and moved to Germany, but then he lived most of his life in France. In fact, Napoleon Bonaparte really thought Lagrange was a phenomenal mathematician, and he was. In fact, he called it Lagrange the lofty pyramid of the mathematical sciences. As I said in the statement of Lagrange's theorem, you have to be careful if the gradient of g is 0. Things can go wrong. We'll never come across that in this analysis here. Well, let's move back now to our maximization of the area inside that ellipse. Remember how it went. We wanted to find the maximum value of the function of two variables f equals 4xy, x and y both being positive, subject to the constraint that it lies on the ellipse. G of xy equals x squared over 3 squared plus y squared over 4 squared equals 1. So how does Lagrange multiplier technique work here? You have your function f and you have your constraint g. The gradient of f, we're going to need that, and that's equal to, well, the function is 4xy. I need the partial of f with respect to x, that's 4y. So the first term is 4yi. Then I need the partial with respect to y, that'll be 4x, so the second term is 4xj. Then I need the gradient of g. Well, I differentiate with respect to x and I get 2x over 9. And then I differentiate with respect to y and I get y over 8. So the gradient of g is 2x over 9i plus y over 8j. So those are my two gradients. Now, the theorem of Lagrange says to find the optimal value, set those equal to each other where there's a lambda in front of the gradient of g. So gradient of f equals lambda gradient of g. Let's write that out. The gradient of f is 4yi plus 4xj, and the gradient of g is lambda times 2x over 9i plus lambda times y over 8j. So that's the gradient of f equal lambda times the gradient of g. We'll equate corresponding components here. The I components should be equal. That leads to the equation 4y equals lambda times 2x over 9. And the j components have to be equal. That means that 4x is lambda times y over 8. So those are two equations involving x, y, and another parameter, lambda. But there's a third equation floating around here, the constraint equation, x squared over 3 squared plus y squared over 4 squared equals 1. So now we have three equations in three unknowns. Let me repeat those equations for you. 4y equals lambda times 2x over 9, 4x equals lambda times y over 8, and the constraint equation, x squared over 9 plus y squared over 16 equals 1. Okay, what was the calculus portion of this problem? It was setting the gradient of f equal to a multiple of the gradient of g. And that gave rise to those equations, and then we threw in the constraint equation, and we had this set of algebraic equations. Three equations, three unknowns. Here's the bad news. In general, these equations are pretty tough to solve. They aren't what we call linear equations. You have to be pretty clever here. The algebra can be difficult and messy. Let me show you how you solve in this equation. This is a class now in algebra. We're doing algebra. The calculus is gone. Lagrange multipliers, for me, are very powerful in use, and the calculus part of them is kind of fun. Take those gradients, set them as parallel to each other. But then you get all this algebra that falls out, and that can be tough going. So let's see how you might solve it. The first equation was 4y equals lambda times 2x over 9, and we could solve for lambda in that equation and get lambda equals 18y over x. Now, we could take this value of lambda and plug it into the second equation. Lambda's 18y over x. The second equation is 4x equals lambda times y over 8. And instead of lambda, I'll plug in 18y over x. So I have 4x equals 18y over x times y over 8. And that means that 4x is 9y squared over 4x, simplifying a little bit. Well, divide by 9 and bring the 4 to the other side, and you have x squared over 9 equals y squared over 16. So that's another equation involving those unknowns, x and y. So we're almost there. We know that x squared over 9 equals y squared over 16. Let's move down to that constraint equation and use this fact by replacing the x squared over 9 with y squared over 16. So instead of x squared over 9 plus y squared over 16 equals 1, the constraint, I now have y squared over 16 plus the same thing, y squared over 16 equals 1. That means that 2y squared is 16, or y squared is 8. Now we're getting somewhere. Y squared is 8. I know what y is. Y is plus or minus the square root of 2, taking the square root of 8. But wait, we're talking about a point in the first quadrant. So let's take the positive value. Y is 2 square roots of 2. So we know what y is. What's x? Well, we have an equation involving x. X squared is 9 over 16 y squared, which is 9 over 16 times 8, which means, and that's equal to 9 halves when you simplify. And so x turns out to be 3 square roots of 2 over 2. Wow. We have our answer. We know what x is. It's 3 square roots of 2 over 2. And we know what y is. It's 2 square roots of 2. That's a point on the ellipse. And with those coordinates, we have maximized the area of the rectangle inscribed in that ellipse. What was that area? Well, it was 4xy, wasn't it? F of xy was 4xy. That was the area function. So we have to evaluate f of the xy pair. X is 3 square roots of 2 over 2. Y is 2 square roots of 2. So we get 4 times 3 root 2 over 2 times 2 root 2. Simplify and comes out 24. So that's the maximum area of a rectangle inscribed in the ellipse. And the rectangle has area 24. How did we do this problem? Let's review some of the steps. We had the equation to optimize, f of xy equals 4xy, and we had a constraint, x squared over y squared, x squared over 9 plus y squared over 16 had to equal 1. In other words, the point had to be on that ellipse, that constraint equation. We took the gradient of f, set it equal to a multiple of the gradient of g, that multiple being lambda, and we had 3 equations involving x, y, and lambda. And then we used some algebra to find those values, and it turned out a unique value came out. Sometimes in problems that are more complicated, you'll have 2 or 3 values that come out, and you have to pick which one's the best. Also, solving those algebraic equations is a non-trivial task, and you might choose to solve them in a different way than I did here in this lecture. There's no one best way to solve these equations. Okay, a little study tip here that you might have wondered about that constraint equation. Remember, it was x squared over 9 plus y squared over 16 equals 1. Well, you could have written that a different way. You could have written it at x squared over 9 plus y squared over 16 minus 1 equals 0. That's another way of writing the same equation. But it doesn't matter really, because the gradient, and that's the part we care about, the gradient will be the same in either case. Now, let me also point out that you could have solved this problem using techniques from elementary calculus. Let me briefly show you how you would do that. I won't go through all the details because it's a little messy. But remember, you wanted to solve for the values of x and y that made 4xy as large as possible, and you had this constraint. Well, you could solve for y, or for x, in the constraint equation and plug it into the value for 4xy. In other words, you know that x squared over 9 plus y squared over 16 equals 1. And given that fact, you can solve for y. That means y squared over 16 is 1 minus x squared over 9, which, if you get a common denominator, is 9 minus x squared over 9. Now take square roots and move the 4 squared to the other side, and you get an equation for y. Y is 4/3 square roots of 9 minus x squared. So what's the function you want to maximize? You want to maximize 4xy, but now I have a value for y in terms of x. So I want to maximize 4x times 4/3 square root 9 minus x squared. That's a standard maximization problem in elementary calculus. Find the value of x that maximizes the function 4x times 4/3 square roots 9 minus x squared. And you could do that and you'll get the same answer, of course. Let me summarize quickly the main ideas of the method of Lagrange multipliers. We assume that f and g satisfy the hypotheses of the theorem. They're nice functions. And we suppose that f has a minimum or a maximum subject to that constraint g of xy equals a constant. And to find the maximum or minimum, you do the following. You solve the equations that arise from setting the gradient of f equal to a multiple of the gradient of g. Gradient of f equals lambda gradient of g, and you add to those equations the constraint g of xy equals c. Now you'll find some examples in the workbook to try your hand. As I've said many times in this lecture, the algebra can be difficult. So you'll have to play around with your algebraic skills here to finally get the right answer. Let me also add that this method is really powerful because it generalizes to optimization problems with more than one constraint. 2 constraints, 3 constraints, etc. And it also generalizes to 3 dimensions. In other words, if you look at an advanced calculus textbook, you'll see Lagrange multipliers in all its glory with a lot more interesting problems than the fairly simple ones we're seeing here with a single constraint. All right, let's now move to our opening example. This was the problem of constructing an open box, no top, of maximum volume given a certain restrictions on the cost of materials. Remember that the bottom costs $3 per square foot to construct, and the material for the sides was $2 per square foot. And we had a fixed amount of money, $1,296. Kind of a strange amount of money. Why not make it $5,000? And I think I mentioned, this makes the numbers come out a little more pleasant. If you put an arbitrary amount of money here, you can get into radical land and things can get pretty complicated. So again, we want to find the dimensions of the box of largest volume subject to the constraint of this finite amount of money. Well, let's label the dimension of the box X, Y, and Z. And of course, we want to find the volume. It's a function of 3 variables. F of X, Y, Z is X, Y, Z. That's the volume of our box. We want to maximize that quantity. And it's a function of 3 variables. Lagrange multipliers can handle this just as easily. There's a constraint. The amount of money is fixed. It's 1,296. Well, what is the constraint equation? Well, the bottom has dimensions X times Y. And it costs $3 per square foot. So the bottom is 3xy. That's the cost for producing the bottom, depending on what x and y are. And 2 of the sides have dimensions x by z, and it costs $2 per square foot for those sides, so we get a 4xz. And in a similar fashion, we get 4yz. So that's the constraint equation. 3xy plus 4xz plus 4yz equals 1,296. All right, we've got our function, we've got our constraint. Let's do Lagrange multipliers. Take the gradient of f and set it equal to lambda times the gradient of g. Well, what's the gradient of f? Well, we have to differentiate each piece. Now, f is equal to x, y, z. So the I component would be the partial of x, y, z with respect to x. So that's yz. So we get yzi, and in a similar fashion, we get xzj, and we get xyk. That's the gradient of f. What about the gradient of g? Well, it's a little more complicated. First of all, we'll have lambda times the gradient of g, so it's lambda times 3y plus 4zi plus 3x plus 4zj plus 4x plus 4yk. I obtained that by differentiating the function g with respect to x, then with respect to y, and then with respect to z. Well, now we have 4 equations and 4 unknowns. Let's stare at those equations for a moment. We equate the I components, and that gives yz equals lambda times 3y plus 4z. And the j components, xz equals lambda times 3x plus 4z. And the k components, xy equals lambda times 4x plus 4y. And then you add to that the constraint equation, 3xy plus 4xz plus 4yz equals 1,296. All right, 4 equations, 4 unknowns. The unknowns are lambda, x, y, z. Let's solve them. Ouch. This is pretty heavy lifting here. This is pretty rough going. This is one of the downfalls, I think, of Lagrange multipliers. Solving these equations can be quite difficult. Some good news, many computer programs now will solve equations even of this type. You can plug them into your computer and it will come up with answers. But we're going to do it by hand. Let me show you some of the early steps you might do to solve these equations. It's non-trivial, but it's algebra. It's not calculus, but it's non-trivial algebra. It's tough algebra. And I don't want to bore you and bog down showing all these steps. And also, it's not obvious that the method I'm doing is the best method. You might have a better way of solving this equation, one to make you more comfortable. But it's a great challenge project. It's a great algebra project to try to solve these equations. Here's how I thought about it. See if you like this method. I tried dividing the first two equations. Divide equation 1 by equation 2. The first equation was yz equals lambda 3y plus 4z. The second equation was xz equals lambda times 3x plus 4z. So let's divide them. So on the left I have yz divided by xz. Well, that means if I cancel the z's that I have y over x. And on the right, the lambdas cancel when I divide, and I have the numerator of 3y plus 4z and the denominator of 3x plus 4z. All right, let's keep going. Don't stay with me here. So my equation was y over x equals 3y plus 4z divided by 3x plus 4z. Now cross multiply. So on the left, I'll have 3xy plus 4yz, and on the right, I'll have 3xy plus 4xz. Oh, that's kind of nice. I'm kind of lucky here. The 3xy's can cancel on both sides of that equation, and I'm left with 4yz equals 4xz. Oh, but I'm even luckier. The 4's cancel, the z's cancel, and I'm left with y equals x. Wow, isn't that nice? I have a lot of information here. Now, of course, you might have already had the feeling that y was going to be equal to x by the symmetry of the problem. But now we know that y equals x, and this is a great step forward in solving this problem. Knowing that y equals x, you can continue these manipulations of the four equations, and ultimately, trust me, you come up with the answer we achieved back in lecture 6, that xy turn out to be equal to 12 and z equals 9. So the maximum volume is that product xyz, 12 times 12 times 9, which multiplies out to 1,296 cubic feet. You know, that's kind of, when I saw that, that's kind of amazing. The volume is the same number as the constraint equation, 1,296. I have no idea why that occurred, but what a miracle. It's the same number. And of course, more important, it's the same answer we had earlier in lecture 6. You might also ask, hey, what's the lambda here in this problem? When you're solving for those four equations, in a sense, you don't care about lambda, but you'll be able to calculate it in case you want it. And one way to find lambda would be to take the equation, say, yz equals lambda times 3y plus 4z, and plug in our knowledge of x, y, and z. So it'd be 12 times 9 equals lambda times the quantity, 3 times 12 plus 4 times 9, or 108 equals 72 lambda. Lambda turns out to be 3/2. So now we know all four, x, y, z, lambda. And of course, the algebra can be daunting. And one way to make sure you did the algebra correctly is take those four values, plug them back into those four equations, and see if they're right. All right. We did only, in a sense, 2 examples today, but they were long examples. Setting up the idea of Lagrange multipliers and then illustrating it takes some time, and it especially makes it difficult because of all that algebra. Let me add that it's a great method when a problem has constraints. So you're optimizing some function, finding a maximum or a minimum, but you have side constraints, 1, 2, 3 side constraints. That's where Lagrange multipliers comes in very, very strongly. The key equation is gradient of f, f's the function you want to optimize, equals lambda times the gradient of g. G is the constraint equation. That gives rise to certain equations, and then you add in the constraint equation, and you have a set of algebraic equations that you then solve. Well, I really like this method, and so in the next lecture, I'd like to look at some more examples of Lagrange multiplier applications. I'll see you then.